Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through this titration tutorial. It's a redox titration between this acidified manganate, which is MnO4-, where you have a -1 oxidation state for this ion. So it's a MnO4-, -1 is the oxidation state of the overall ion. This is equal to the combination of the individual oxidation state for one manganese and also 4 oxygen. Oxygen, when bonded to something else, has an oxidation number of -2 when it is not bonded to itself. So manganese there is -1 plus 8, manganese is +7, which your calculator will not show you the plus, but the oxidation number must have the plus there. So this permanent pale pink color is a result of this MnO4- not getting oxidized anymore. So one extra drop of these MnO4- is not reacting anymore. So why is it not reacting anymore? Because there is nothing else to be oxidized by this oxidizing agent anymore, which is why the reaction has finished, and that is when we know there's the end point there, which is why we don't need any indicator. This reaction is what you will call self-indicating because of this rapid and also drastic color change on its own. Now P is obviously this manganese 7th ion, so it's a purple, dark purple color looking solution. I think the experiment that you did and the demonstration that I'm going to show in the latter part of this video, it actually involved a dilute solution of these which look quite light purple, but in reality it's actually very dark purple. When concentrated, we read above the meniscus under such circumstances. So this solution was prepared by converting all the manganese in that sample, which was an alloy. So it's a mixture, so that mixture does not contain everything in the manganese. It does contain something else other than manganese. So we can be thinking about simple diagram. Always draw a simple diagram to see what is happening. Draw and see what is happening. If you can see what is happening, things become much easier rather than you just using random formula and doing some random calculation. So all of these, which is what it has manganese, but not all of it is manganese, and then you react it such that you get everything, which is MnO4-. So that is MnO4-, and then you make it up to 250 cm3. So this is 250 cm3 of this purple colored solution here. And you're gonna take out, so this thing here is MnO4-, this thing here is P, so that is P there. Usually we'll be thinking about taking out 25 cm3 of this. However, this question said put P in the burette. So I'm gonna draw a burette because I know how to read the questions. This goes in the burette, so P in here. So this is in the burette and not taking out 25 cm3 in by a pipette. Okay, so just be very careful there. So this Q is the iron 2 sulfate, and where does Q go into? Q is here. It contains iron 2+, and you're going to oxidize the iron 2+ to iron 3+ until there is no more iron 2+ remaining. Everything is iron 3+, then one extra drop of this purple colored MnO4- is going to remain permanent pale pink there. Anyway, they did tell you to always take your readings using the top of the meniscus. That is what I would do as your supervisor as well. So just keep an eye out for these kind of little things. Put pipette out, not just put, but pipette out 25.0 cm3 of Q into a flask, and then you just do your titration. Okay, so I have actually done these titrations, the demonstration of which I will just show in the latter part of this video. So we're going to do a rough titration here. Rough titration means we don't care so much what the actual reading is, because if you don't know roughly where it ends, then you're not going to be able to work out the exact titer. By right, you should have a white tile at the bottom, and that should help you to see the color change better. So as I already recorded the initial volume, I'm ready to just open the tab fully. As you could see, it remains kind of like kind of colorless as well, because there is still a lot of iron 2+ left in there. The iron 2+ get converted to iron 3+ in solutions, which is also very pale, kind of pale yellow. But because this is a very diluted solution, it doesn't look that colored at all. But when there is no more iron 2+, when everything has been converted to iron 3+, then extra drop of these is going to make the MnO4-, the one that gives you responsible for the purple color, to remain in there unreacted, and therefore you will get a permanent pale pink. or purple, depending on how much you have. So we're just going to continue, and you still like colors. You see there's no color change at all, but we're just going to stop when it changes color. Okay, so getting there, I think this is about it. Okay, so this rough title, I wasn't being drop by drop. I wasn't doing it drop by drop because I'm doing a rough titration. As you can see, the color now, it is colored. It is colored, okay? Hopefully you can see it is colored. In comparison with this original solution, which was not colored. So we can be sure that this has just turned, but this can never be your exact title. This is your rough title. If I read the reading first, what do I have? I'm reading above the meniscus because this is supposed to be a dark color solution. It's quite hard to read. We always read above the meniscus. That one is, and give me a minute. We read above the meniscus. We read above the meniscus 23.123, 23.3 cm cube. So for my rough title, let's see if I lift this up a little bit, and hopefully you can see it against the white background. 23.3. Not too sure if that is clear. You read above the meniscus, so 23. Is that reading very well? Probably not. But you know, you can see that 23 is on top, 24 is at the bottom. So you read from top to bottom. There's around 23.3 if I read above the meniscus. Okay. So 23.3 minus or take away 0.5, I get 22.8. This is my rough titration. I always make it a habit of doing a rough titration. Now I know 22.8 cm cube is my rough titration. I should probably fill out my burette because, you know, starting from 20 something is a bit dangerous and tricky. So let's start from a nice number. I've got it to around 14 point something there. I should remove a little bit to go to 15. Again, I'm reading above the meniscus. Don't mind that you can read this because it's quite light, but you should imagine a scenario where you're given a much more concentrated solution where this is a lot darker. So you need to read above the meniscus, and reading above the meniscus here give me 15. So I'm reading above the meniscus because this one is supposed to be a dark color KMNO4. Reading above the meniscus give me 15.0 cm cube. So this is my initial volume, and I'm ready to do my first exact title. So 15.0 for my exact title, 15.0 plus 22.8, so give or take 23, 23 plus 15, 23 plus 15 is 38, but 38 would be in excess, but not a lot. So if I take away 2 cm cube or 3 cm cube, just now I didn't overshoot by a lot, so I'll just take away 2 cm cube, so 38, because 15 plus the rough, and then take away 2 cm cube, 38 minus 2, 36. So I will slow down. I will do drop by drop when I reach 36, but I will not do drop by drop from the very beginning because there will be a waste of time since I already did a rough titration. Anyway, let me just, we're supposed to do 2 exact, right? So I'll just head out what I need. So we need another 25 mil, 25 cm cube of this iron 2 plus here. So this one is going up quite quickly actually. So ejecting there. So this thing is a colorless or kind of pale green supposedly, but very dilute, so it's kind of like colorless. So you're reading below the meniscus, yeah? So be careful. You only read above the meniscus when it's a dark color solution, but you read below the meniscus if it is a colorless solution. So this is 25 mil, 25 cm cube. So if you can see that below the meniscus, okay? Now this is my conical flask which I rinsed with distilled water earlier. Should have been a bit more gentler, okay? So always be gentle with glass. So let gravity does its job, and when you reach the very end, only then you do the tapping. So let gravity does its job first. 1, 2, 3, 4, 5, 6, 7, okay. Now again, we don't need indicator, it's self-indicating. 15.0 is where I'm going to start this exact title. plus the rough is going to give me roughly 38, but this is rough, so 38 cm3 final volume is going to be rough. I take away 2 cm3, I should stop around 36 cm3, then I do it drop by drop. And I know, okay, so 36 cm3 is around here. So 36 cm3 is around there. So I'm not going to slow down, I will just let it flow full speed until it reaches 36, then I will slow down, okay? So when it reaches 36, then I will stop, okay? I'm not wasting time that way because I roughly know where I'm fishing already. So it reached 36 already, so now it's 36. You see this thing is a bit, kind of like a bit colored now, but then we know this is still iron 2 plus in excess because the KMnO4 is still not in excess. If I swirl it, as you could see, it go back to this color, which is not colored at all. Okay, so it's slightly darker now because of the iron 3 plus being formed in solution, but you don't have excess KMnO4 yet. Your end point is when you have a permanent pale pink, because one extra drop from here will not go away. One extra drop from here will remain there. You get a permanent pale pink color. So let's focus on that. Let me just zoom in on that. So I'll just do drop by drop now. So let's just focus on getting this thing drop by drop first. So you want your hands, you're around 2 cm away. So spend some time getting the control right. So I already got it drop by drop. And you want to swirl. You want to let it swirl. I'm right-handed, so I'm swirling the conical flask with my right hand, and my left hand is continuously on the tap, and then when it changes color, I stop. I don't do the reading yet. I don't care about the reading. Do not take your eye away. So just keep on swirling. So this is quite slow actually. So just keep on swirling and swirling, hands on the tap, and when it changes color permanently, when you get a permanent pale pink, then stop. Okay, so it's getting there, I think. Is it there yet? Is it there yet? I think it's there already. I think it's just there. I think it is there. Just give me a minute, I've got one drop there. I think I've just reached the end point there, so that is kind of like pale pink. Kind of like permanent pale pink, not too sure how well the contrast is. It's very, very light because the solution is very, very dilute. But it is quite colored when you compare with this thing here. So this thing is supposed to be a little bit colored. This thing is totally colorless, kind of colorless, okay? So if I put it on a white background, you can hopefully see the difference between the two. Okay, before I add one extra drop, I should take the reading first, just to be safe, just so that I have a record of what is going on. I read above the meniscus. This one is 36.5. 36.5 if I read above the meniscus. You read first. Later on we can decide on whether we're going to use it or not. Okay, so that is 36.5 if I read above the meniscus. I don't think that is eye level actually. So hopefully that is eye level now. So 36 and then 37 at the bottom. You read above the meniscus, so 36.5 cm3 there. So 36.5, and that should give me 21.5. 21.5 for my exact title. What I'm going to do is I'm just going to add one extra drop and see what happens. So let's add one extra drop. 2 extra drop and see what happens. It's quite light, yeah. It's really, really light, but hopefully you can see that it's getting a little bit more pale pink now. This is a permanent pale pink or permanent pale pink because this is supposed to be purple. When you only have one extra drop, it's not going to be purple, it's going to be a little bit pale pink as a result of it. So I'm pretty sure what I've gotten previously was quite accurate already, but this one is just 36.7. So this is 36.7. So I'm going to put it at an angle a little bit, so 36.7 there. So just now I got 36.5, 36.7, so still pretty close. I'm just going to take note of it somewhere, just so that when I do my exact titration later on, then I can think about what is going on. So that was my second one. So it was 21.5. Let's do a third titration, which is going to be our second exact one. So I fill out my burette first. And I think I'm going to start. Then I'm going to start from an easier number. So that is 17.0. So that is 17.0. So let me just make this upright. So 17.0 there. So reading above the meniscus, 17.0 cm3. Alright, so 17.0 is where I'm going to start. I have run out of conical flask, so I will just put this away. No, actually, I'm going to keep this. This was in larger access. I'm going to throw it away. Rinse it with some tap water. So after you rinse with tap water, I'm just going to rinse it with some distilled water. And then throw it away. I rinse a second time with distilled water. A little bit of distilled water left in there will not affect the titration volume because the mole of the stuff that you pipette out is unaffected by the amount of water left in the conical flask, and therefore it will not affect your burette titer at all. So let me just zoom that out a little bit. Nope, I don't need to zoom out. So this is my pipette there. I'm just going to eject out here. We read below the meniscus because this is not a colored reagent. So below the meniscus you can see I think it got a bit of air bubble, but I think you should probably check a bit more, suck a bit more. That should do the job, I believe. So there's 25 ml there, 25 cm3 from this 25 ml pipette. So eject it out into the conical flask. We're ready for our second exact titration. You're doing an actual practical. You want your exact titer to be almost identical, as identical as possible to the actual value. Okay. So you want it to be like what just now? 21.5 was my exact titer. So 21.5 was my exact titer plus my 17.0. I don't have a calculator with me, but I can do this manually. 5, 8. So I should get 38.5 cm3 as my exact titer. But I don't want to, only slow down to 38.5. I want to slow down maybe at 37, and then I can do drop by drop. Okay? Because I know I already taken away like 1 cm3 there. So I was supposed to end out at 38.5 with the exact titer, but I will stop when I reach 37 degrees Celsius. Not degrees Celsius, 37 cm3. I will stop. Then I will do it drop by drop. Okay, so here you see it going a little bit pale pink. Let me just bring it around closer, and then you can see what's going on. You can see it going a bit pale pink there, but then we can swirl it around, and you can see the pale pink color disappears. You want it to be a permanent pale pink with one extra drop. So I'm just going to that was what we're supposed to get, like permanent pale pink color. But then this is what we have at the moment, which is kind of like the color of the iron 2+, which is like kind of colorless, isn't it? Okay. Anyway, so let's get your drop by drop done first. And then I'm just going to swirl. I'm right-handed, so I swirl on my right, and my left is on the tab. I don't look at the volume. I never look at the volume for exact titer. I just eye focus as I swirl. My eye is focused on when it changes color. So one extra drop will give me a permanent pale pink color. I think it's getting there, really close. This is our exact titer. We don't want to waste time. We don't want to waste time to do 1000 exact titration. I think it's just about changing color with the next drop, maybe. It's very, very light, isn't it? Come on. Come on. Yeah. I don't want to reset. Has it changed? I probably need one extra drop. I think it has slightly changed because it's kind of like getting pale pink now. Okay, maybe one extra drop, but this is, no, I think it has changed. It has changed. Not too sure how clear it is, but you know, one is supposed to be the original colorless, and this is a bit pale pink. This is a bit pale pink there. It's probably better on the contrast there. But let me just read the reading first, okay? Because that's important. If I read above the meniscus, there is 38.6. Read above the meniscus there is 38.6. And again, there's some sort of margin of error, right? If you don't think the color is that obvious, then you know you can go a bit further. 38.6, not too sure how well that will read. So read above the meniscus, so 38.6 there. 38.6, yep, that is what my reading is, 38.6, okay. So what do I have? 38.6 minus, so one decimal place throughout, 38.6 minus 17.0, I get 21.6, and they are within the 21.5 that I obtained previously. But yeah, I mean, these two really light color, but in reality, in the real exam, perhaps when you have more concentrated KMNO4, the color will be a lot more obvious. Okay, if you are not too satisfied with this color, you can of course add one extra drop and see what happens. So I'm just going to add one extra drop to this. One extra drop is probably like 0.05 cm cube. Oops, I've added two extra drops, and you can see the pale pink color a bit better now. So it's gone a bit darker. The contrast is not helping us that well, to be honest. So that is still 38.8. So even 38.8 is going to give you 21.8, but that is beyond what is acceptable already. So it's really hard to tell, right? Which one is more exact, which one is not exact. But based on what I have seen, I could see the color change because I have my colorless solutions, well, nearly colorless solution to begin with, and then when it changes color, give me a permanent pale pink, that is where I stop. So I think my 21.5, my 21.6 is perfectly acceptable as my best titer, which I'm going to put a tick on it. And when I do my averaging, I have to show my working average 21.5 plus 21.6. I use a bracket because a lot of students, they don't use bracket and then they end up calculating the wrong stuff in the calculator. And what is important is I have two readings, so when I average, I divide by 2. If I have 3 best reading, if I have 3 ticks, all of them, they are within plus minus 0.2 cm cube for your O level, GCSE level, or IGCSE level titrations. You know that plus minus 0.2 cm cube is the maximum accepted error margin. But of course, in the real titration, you want your titer to be as exact as. Okay, I'm back. So from those titration that I have done, so my rough titer was started with 0.5. So it was just based on the video that I have just shown you on the titration bit that I had just done. So I did a first rough titration, and I have 2 exact titers that I really want them to be as close to each other as possible. In fact, I want there to be no difference whatsoever. This is the final reading. So final minus initial, I get 21.5 cm cube for my first exact titer, and I get this 21.6 for my second exact titer. You want ideally this exact titer to be equal to each other, but then we are only humans. We are within experimental errors based on this 1 decimal place burette reading. You are allowed up to 0.2 cm cube plus minus error margin. Of course, the better you are as a chemist, the smaller is this error margin, as close to 0 as possible. But then, as I said, due to the error in the accuracy of the burette, 1 decimal place accuracy, we could have up to plus minus 0.2 cm cube that accepted for our best titer. Okay, I already ticked the best titration results. So using these results, the average volume of P, this goes into the burette. That was your KMnO4, the purple color solutions. So I need to show my average. Okay, so showing the averaging is quite important process. So make sure you use a bracket in order to do this thing on top, because once you make a mistake without the bracket, you will be making a really silly mistake that there is no turning back for you at all. Okay, if you make that mistake. This comes down to 21.6 cm cube. It also has to be 1 decimal place for an appropriate number of significant figure for a burette titer. The volume of Q used, that was from the pipette. If you look the reading from the pipette, it was 25.0 cm cube. It was to 1 decimal place. Fairly accurate apparatus, this pipette, because it's just that it can't measure any other volume apart from the fixed volume that it was designed to measure. 25.0 cm cube, that was the pipette I used in this experiment. So for these 12 marks, there are around 6 marks for accuracy. And then there is like a 3 mark for concordance. Concordance means your decisions in taking your exact titers to be within the acceptable error margin, although of course you want it to be as close to zero difference as much as possible. If I'm not mistaken, you get 1 mark for, I forgot how they're going to split out the other 1 mark. I think 1 mark for 1 decimal place throughout. So if any of your burette titer is not 1 decimal place, you will lose 1 mark. So that is 10 marks. There's 2 more marks. I forgot what the 2 marks were for already. Okay, I remember. It was to do with the difference, so final minus initial. But then 1 mark is for the correct placement. So some student they put the final reading onto the initial reading, or the other way around. So correct placement based on the reading of the label should give you 1 mark. And then of course calculating the difference, final minus initial volume, that should give you the other 1 mark as well. Your accuracy is based on comparisons with your supervisor results, which in this case, if you are my students, your result will be compared to mine. This value is not always fixed. It depends on the batches of the chemicals that were being prepared. Let's start with the calculations. So we want the moles of iron 2 sulfate present in the volume of Q used. This was pipette out. We pipette out 25.0 cm cube. So the mole of the iron 2 plus N equal to CV. Do not forget mole per dm cube concentration. The volume that has to be in dm cube. Number 1 mistake, cm cube to dm cube, you need to divide by 1000. Rookie mistake, but once you keep on making it, you are never going to improve unless you keep an eye out for this kind of thing. So follow the level of accuracy. Appropriate number of significant figure is a decision making that you need to take into account. This is what my calculator show me. However, taking into account this level of accuracy, 1, 2 and 3 significant figure, 1, 2 and 3 significant figure, this is just 1 significant figure. It is too little. You need to think when your calculator cannot think. You need to think on behalf of your calculator. Using your answer from B, calculate the moles of MnO4 minus present in the average volume of P required. In your titration, how much of the volume from P actually reacted with the iron 2 sulfate. But then we were also told about mole ratio. So we are not really doing theory. We are doing our calculations based on the information given. So P is the manganate. So MnO4 minus in the titration is to the mole of the iron 2 plus. Our information is 1 mole of MnO4 minus is to 5 moles of iron 2 sulfate. This is how I always like to set up my mole ratio from the balance equation from the information given. On the other side, this is a solution. And then at the bottom, this is a solution. So this go back to N equal to CV, where I already talked about the importance of units and to keep an eye out for the conversion of CM cube to DM cube. So we know based on the average volume of P required, but they are not asking for concentration or anything. They're asking for the moles. So I just need to find the actual mole of MnO4 minus that reacted with this actual mole of iron 2 sulfate. So I just put in my value and I bring this up. As I bring this up, I do not change anything on this left hand side. So it's still 1/5 because I'm just bringing up the bottom to the top there. I do not change anything in this cross multiply example because this is just mathematics there. So of course the mole of MnO4 minus then is just equal to whatever answer I had just now time 1/5. Oops, hang on. So 2.00 times 10 to the minus 3. Make sure you know how to key that into your calculator. And I get 4 times 10 to the minus 4. Again, the calculator does not think on behalf of you. You need to think on behalf of the calculator. 3 significant figure to have appropriate number of significant figure based on the data, based on the data, based on the data significant figure. Now, using your answer from C, calculate the number of moles of MnO4 minus in 250 CNK of P. Remember, this is not your usual 250 and then take out pipette out to 25. Instead, that was your burette. So inside your burette, we only had 21.6 cm cube best titer. This was P. P was KMnO4 because you knew how to read question. So 21.6 cm cube best titer P. So in this 21.6 cm cube of P, we have 4.00 times 10 to the minus 4 mole of P. So therefore, in the 250 cm cube of P, we're going to have more mole because they have the same concentration, as I was just filling in my burette from the solution that I have made up to 250 cm cube. So times 250 divided by 21.6. This is not a straight multiple of 10, so you need to be very, very careful and think about your direct proportions because it's all about reading the questions to 3 significant figure just to be consistent. That is actually the mole in the whole of that volumetric flask. The 250 cm cube was how you made up the solution up to in the volumetric flask. Not AS, but year 9 alternative to practical, year 9 mole calculation stoichiometry topic. Using your answer from D, calculate the mass of manganese in this 2.12 gram. We know that is a mixture. We do not use this 2.12 gram here. We are told that the relative atomic mass of manganese is 55. If you think about it, all of these 2.12 gram, which is a mixture, all the manganese go in there. So, the mole of manganese is the same. So, manganese going to MnO4 minus. If you think about it, that is manganese 0. That is manganese plus 7, as I showed you earlier in this lecture, well, in this tutorial, to be honest. There is 1 time manganese, and there's 1 time manganese. The mole ratio is going to be 1:1 based on the formula. So therefore, the mole of the manganese is equal to the mole of the MnO4 minus in the 250 cm cube altogether, because all the manganese here go into here. So we have 4.63 times 10 to the minus 3, and this is equal to the mass of the manganese, mass over mR, because this is to do with reacting mass here, and you're not given periodic table, hence you're just given the value there. Bring up the 55, so the 55 is multiplied by that 4.63 times 10 to the minus 3 times 55, and I get 0.25465, too many significant figure. Round it up to 3 significant figure there to be appropriate number of significant figure. Using answer from E, so out of the 2.12 gram, which is a mixture, how many percent of it is actually manganese? So out of the 2.12 gram, only 0.255 gram is actually manganese. So, time 100%, the gram and the gram cancel out. And if you follow the math, and if you follow year 9 chemistry on percentage purity, percentage compositions, you would understand this perfectly. To 3 significant figure is a percentage unit there. Okay, so that's the end of that 70-mark practical questions. The practical itself took quite a bit of time, but you should be able to do the calculation fairly easily, as one question led you to another, unless you don't know how to do a year 9 mole calculations. Okay, thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel, and follow me at ptet.chemistry. That's at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. I'll see you in the next tutorial video.